In the previous episode, we managed to make our CPU recognize and execute its first instructions. We are using the program counter as an address into the program memory, where we read out 8 bits worth of instruction per cycle. The 2 bits at the bottom of the instruction decide whether we simply step to the next instruction or perform a relative or absolute jump. The 4 bits at the top are used to decide where we want to jump to. So we've already used up 6 of the 8 bits in the instruction, but our CPU can't really do anything yet besides just jumping around the program memory, which is pretty boring. So we don't have a lot of bits to work with to make things more exciting. Let's take a quick step back and think about this for a second. So if we want our CPU to have 4 registers, we would need a 2-bit number to specify which register we wanted to work with. And let's assume that most instructions would need 2 registers to work with. For example, add 2 registers together and store the result back to one of them. That means we need a total of 4 bits per instruction just to pick which registers to work with. The remaining 4 bits we can use to encode what operations we actually want to do. But 4 bits really isn't a lot. That's only 16 different operations we can choose from. And we might want to have more than just 4 registers in the CPU. So clearly 8 bits isn't going to cut it for what we want to do. Instead, we're going to want to use 16-bit instructions from now on. That would allow us, for example, to have 16 registers in the CPU and still have enough instruction bits for 256 different operations, which seems like a much more interesting playground than what we have now.
So this is the program counter and the program ROM that we've been building up so far. And we hooked up the various control signals of the program counter up here to the outputs of the program ROMs. And we were able to run a small program with that. Let me power this up. So if we bring the system out of reset with 4 clock cycles, you can see that the program counter starts counting up. And we have various instructions in here. For example, this one here is a relative jump, which is indicated by this 1 here on the select input. And it's going to jump, I think, 3 instructions forward to address 4. There we go. And there's a bunch of knobs, which the program counter just skips over. And then address 7 is another relative jump, but this one backwards to address 2. And then we keep going all the way. And then at the very end of the program here, we have an absolute jump to address 0, which basically causes the program to go back up to the top again. And the instruction was only a single byte because the flash down here has an 8-bit output port. So basically the most we can get out of this flash by when we presented an address is 8 bytes of data. But we would like to extend this to 16-bit instructions so we have more flexibility and can have a wider range of operations. So let's try to do this. First, let me disconnect power and isolate this board down here so we can work on the program flash and the way we pull data out of it. Disconnect the program counter. Then the absolute jump address, the relative jump address, and finally the selector, the mode selector for the program counter. So now that we've disconnected the input address to the program ROM, let me wire that up to address 0 so we have something to look at and we kind of know what is at that location in the flash memory here. So as a refresher, let's take a look at what's actually at address 0 in the flash memory. So it looks like the number 16, and then at address 1, there's a totally different number. So in a sense, what we have to do if we want to have 16 LEDs over here, which show the contents of both address 0 and address 1 at the same time, we would have to do something like read address 1 from the flash, store it in a separate chip, and then switch over to address 0 and read that out of the flash. And then the combination of what the flash currently presents, which is address 0, plus what is in the separate storage chip, which is what we read before when we selected address 1, gives us basically this 16-bit number of the value at address 0 in the lower 8 bits and the address 1 in the upper 8 bits. One convenient way to do this is using a latch chip. These are very similar to flip-flops, but they have some slightly different characteristics, where flip-flops store the value that is presented as your input on the clock edge, usually the rising edge for these kinds of chips. Latches are slightly different. They're much simpler than a flip-flop. When the clock input is high, the latch becomes transparent, and everything that shows up at the latch's input will immediately be transported to the output. The latch just looks like a buffer. But when the clock goes low, the current state of the latch is latched, hence the name. And whatever you do at the inputs won't change the output. So this gives us an interesting opportunity to take what the flash chip is producing, feed it through the latch, and as long as the clock input of the latch is high, the output immediately reflects what's coming out of the flash chip. But then when we take the clock input low on the latch, the output will basically remember what came out of that program ROM chip here. And we're free to change the address on the ROM chip here and basically pick a different location to be read out, but the latch is still going to remember the previous data that we read out. So the combination of what this ROM chip produces and what is still stored is going to give us the 16-bit number that we want. So for starters, we are going to need another 8 bar graph LEDs and also some resistors to put in front. And let me disconnect power here. And first of all, let's arrange the second set of LEDs over here on the right side and wire them up to ground so we have something to connect to. First, let me disconnect these existing connections here. So down here, we will have the least significant bits of what we are reading out of the ROM chip. We also need to hook up some resistors here. Now this latch chip here is built in a way that on the left-hand side are all the inputs and on the right-hand side are all the outputs. What we're likely going to do is just place it somewhere like this and then hook up the outputs as they come out of the ROM here to the inputs of the latch, but then also wire them up to one half of the word over here. And then the other side, we're going to hook up to the other half of the word over here. What this means is that 8 bits of the word we're interested in are going to come in from the top here, and the other 8 bits are going to come in from the bottom. So we'll have to flip one of these LEDs around. So something like this. And then we can also reuse this ground connection here on the LED over here. And we need to wire up ground up here as well. Something like this. Let's check if the LEDs work. Perfect, that is all working. Next up, we want to hook up this latch chip here, which we're going to place here in the middle. Something like this. And that thing needs power and ground. Now the latch also has an active low output enable pin. Since we're always going to want to look at what the latch has stored, let's just pull that low. Now pin 11 down here is the latch enable input, which is basically the clock of the latch. And if we pull this high, the latch should be transparent, which means it will basically continuously store whatever is at the input and immediately present it at the output. And then when we take this latch enable line low, basically the connection will be broken, the outputs stay in the state they were, the inputs can change however they like. So let's maybe start out wiring up the simple part, which is basically the output side of the latches here to the left 8 LEDs. I've prepared a few wires that we can use to do that. Let me get rid of this latch enable signal here for the time being. We'll add that later. Might actually be easier to start from the most significant bit here and work our way to the right. Next up, we'll want to bring the outputs of the ROM chip here over to the inputs of the latch. I've also prepared some wires for exactly that purpose. Now let's maybe start with the rightmost pin, which is bit 2. Then bit 1 and bit 0. And then we have 5 more bits that we need to hook up. So that's 1, 2, 3, and then bit 4, bit 5, and bit 6. That's actually bit 6. And bit 7 is here. All right, perfect. That's pretty much it. So that should give us a connection to the first set of LEDs here through the latch. And now all we need to do is bring over these connections to the other set of LEDs as well. I've also prepared a few wires for that, so let me do that. Start out at bit 1. 2. Let's actually move those a bit closer in. Then bit 2. Then bit number 3 up here. And bit number 4 over there, and then bit number 5, which also has to go in somewhere there. Now these wires are pretty challenging to connect properly because the isolation is it's pretty thick, so quite difficult to have them go all the way next to each other. All right, so bit 6, getting closer to the last one. So let's actually do bit 7 first. That might be easier, like so. And then bit 6, the next one over. And ideally, we now have 8 connection points on the breadboard up here where we can connect the least significant bits of the instruction, and we have 8 connection points here where we can connect the most significant bits of the instruction word. So let me hook the latch enable back up, which is right here, and let's wire it to high, which means the latch is going to be transparent and continuously storing whatever it sees at its input. And let's power this up and let's check if we can still read from the ROM chip and have the results appear on the LEDs over here. That looks pretty promising. So as you can see, we have the same pattern light up on the upper and the lower byte of what we're reading out of memory. And this is because the latch enable signal is high, so the latch is transparent, it's like a buffer. So whatever is the input of the latch, which is shown on the right-hand side here, is also fed through the latch immediately and presented at the output. And if I change the address line to a 1, so we're reading from the higher address, you can see that both halves of the output change simultaneously, which is again down to how this latch works. But now if I pull the latch enable signal low, nothing changes immediately, but now the latch is in latching mode. So if I change the address over here, we should see the upper byte stay put as it is right now, because that's being fed by the latch, and that it has just memorized what it has shown before. But the lower byte should update to whatever comes out of the chip. And as you can see, that's exactly the case. So the most significant byte, the upper byte, hasn't changed, but the lower byte is updated to show whatever comes out of the memory chip here. So now what we should be able to do is actually cross-connect the least significant bit of the address, so address line 0, which picks between odd and even bytes in memory. And we should be able to cross-connect it to the latch enable signal. And what we should be able to do now is basically pull the latch enable high, which is going to put the latch in transparent mode, so we get like a replication over here. And then we can choose any other location in memory. Let's maybe use memory location 2. Now if we pull the latch enable low, you can see that the upper byte remembers what came out of the memory when that signal was still high. So that was basically the least significant bit of the address set to high. And the lower half of the output has updated to whatever the memory is producing now, which is the address with the least significant bit, address line 0, set to 0. And by doing this, just by toggling the clock, we can use the fact that actually in a single clock cycle, the clock toggles to high and to low. So it has 2 phases in every single clock cycle. And we leverage this here by using the high phase of the clock to read out the upper half of the 16 bits from memory. And then in the second phase of the clock, where the clock actually drops to 0, the latch goes into latching mode and remembers what came out of the memory when we revved the upper half. And then during the low phase, we actually read out the lower half of the memory, and we present this immediately at the output over here. Cool, so now that this works, let me bring back the program counter and clock generator circuit, and we'll hook it back up to this program memory board here. And then let's see how we can make use of these additional bits that we've gained for the instructions. Okay, here we go. So the cool thing now that we have 16 instruction bits, we can use the upper 8 bits of the instruction to drive our relative jump offset or the absolute jump address instead of just using the upper 4 bits of the instruction. That's going to give us a much wider jump range, which is super cool. One of the problems is that we only have space to connect one thing down here beneath the LEDs. What we'll probably want to do is actually bring these connections here for the upper half over to this side where we have some spare room, and then actually hook these things up over here. So let's start with that right away. Let's just wire up the relative offset down here. Now that we have 8 bits from the instruction to use as the relative offset, there's no more sign extension we need to do where we replicate the topmost bit to cover all the 8 bits of the offset, which is what we had to do when we only had 4 bits. But now, since we have a bit for every single wire here, there's no more need to do that. Then we have the absolute jump address, which we are going to wire up to the same lines. So let me bring the 8 upper bits of the instruction over here. Then later on we'll use a proper DuPont kind of cable with like one connector here, so we don't have to fiddle with these like individual connections all the time. But for the time being, that's going to be good enough, I think. All right, so that's the upper 8 bits connected. We also have this select line here, which picks between the stepping, relative jump, and absolute jump modes of the program counter. And let's just bring this down again, and let's just use the lower 2 bits of the instruction as we did before. And now the cool thing is that these 2 lines allow us to choose all the different control flow modes we have supported in the program counter here. And then the uppermost 8 bits basically allow us to jump everywhere in the program at the moment, both relatively to the current program counter, but also in absolute terms to a fixed address. But still we're left with 6 bits in the current instruction which aren't used and which we'll be able to make use later on to do other things like picking register slots and register addresses and similar things. So it's going to be super interesting to build something with this. Then next up, we made a big deal about actually using the clock to drive the least significant bit of this this flash chip, and then also use the clock to drive this latch over here. But this also means that we now have to actually wire up this clock to the rest of the circuit. Let's use a longer wire here. Let's plug it into the latch enable, which is basically our clock signal. And then we'll bring it all the way up to the clock input of the program counter register here, which is connected to the clock of the clock generator board up here. So we make our way all the way down here. And that clock is now driving both the latch enable as well as the least significant bit of the flash. Now this connection here we don't need anymore. Last but not least, we actually have the actual input address to the flash memory here. The only difference now is that the least significant bit of that is already predetermined by the clock, but we still have the next 7 bits that we can feed from the program counter here. So let's remove these temporary wires here, which are no longer needed. And now we can bring this program counter back down here. So we'll skip the least significant bit of the program counter because we're always delivering both bytes, the one where the least significant bit is 0 and the one where the least significant bit is 1. And we're basically delivering them as a single 16-bit word in one go. So basically whatever the address is in the program counter, we're always rounding down to the next multiple of 16 bits or 2 bytes. And then we produce both of those bytes. And this last one we just leave floating here. And now the only thing left to do is actually hook up power and ground to this board here. And we should be ready to power this up and take a look at how things work. As a first test, let me actually pull the select lines here. Let me pull those low so we're in stepping mode. So the program counter keeps incrementing. And this will allow us to basically first test the operation of this new 16-bit program memory just by stepping through the individual locations. And then later on, we'll adapt things and actually make use of this line and update our program and our encoding. So let me power this up. And right off the bat, this actually looks kind of okay. We're at address 0, and we're basically producing byte 0 and byte 1. The same ones we've seen before when we did the individual tests with the address 0 manually wired in. And now the interesting thing is we're still in reset mode, so we'll stay at address 0 for 4 more cycles. If I hit the step button here, look what happens. The clock line goes high, which means the latch is going to go into the transparent mode, which is also why you see the same output on both of these bytes here. They're identical because right now we're looking at, because the clock is high, we're looking at the address where the least significant bit is high. So that is address 1 in this case. And we're reading the byte at address 1 and we're feeding it into the latch. And because the latch is transparent, it's showing up at the latch output as well as the current location. But when I release the clock, the lower byte here updates because the clock has now gone down to the low state, which means the latch down here has gone into the latching state. That also means that the output that the latch produces still reflects to whatever was there before, so that's still the upper byte. But now that the clock has gone low, the least significant address line here that goes into the flash chip has dropped low as well. So now we're reading the byte at address 0 here. This is the one you see over here. And this is going to happen on every clock, basically. Okay, so now we're out of reset, and now we're down to the interesting part. So look what happens when I hit the step button. The program counter jumps to address 1. This doesn't really do anything yet because we are ignoring the least significant bit of the address because we're always producing both bytes at the same time anyway. So nothing happens right now. But when I hit the step button again, this program counter will go up to address 2. And as you can see, we're now reading address 3 out of the memory. The address the program counter is producing is address 2. So we're reading the current program counter plus a 1. So this is byte 3 that is coming out of the memory. And when I release the step button, the clock goes low. And here we're basically reading address 2 again. So now we're at address 2, but when I hit the step button, this goes to address 3, which again, because we're ignoring the least significant bit and we already had produced bytes 2 and 3, it's just going to produce the same thing again. So we're reading byte 3 again, it's getting latched in at the top, and then when I release the step button and the clock goes low, we have again the same output here. But then the next step, when we go to address 4, you can actually see there's a different pattern coming out now because this is the byte at address 5. And then when I let go of the clock, the lower byte actually updates to whatever is at address 4. So right now we're looking at address 5 and 4 in parallel. So in a sense, all the odd numbers of basically program counter addresses are kind of not interesting to us anymore because we're always reading 2 bytes at the same time. So this least significant bit is kind of useless for us. So what we can do is, remember we have this step size line here, which allows us to choose how many bytes we want to advance in normal stepping mode. And this is super handy now because we can actually, it's set to 0 at the moment, which is configuring it to just step single bytes. If I configure this to a 1, it's actually going to count up by 2 bytes at the same time. So if I hit the step button, watch what happens to the program counter here. It has jumped up by 2 bytes, and this also means that we're immediately looking at the next interesting address down here. So right now this is address 6, which means that down here we are reading out address 7 at the moment and storing it in the upper half of the instruction word. And when I release the clock, we're reading actual address 6, and this gets presented at the lower end down here. So whenever I hit the button now, we get a new instruction word, and we can step through the instructions like this. And then at some point, it's just garbage in the memory because we ran past the old program that's still stored in this flash here. So we've updated our program memory to fetch 16 bits worth of instruction in a single cycle, and the program counter to walk through the program in 2 byte steps to account for the wider instructions.
In the next episode, we're going to take a look at wiring the select line of the program counter back up to the instruction, and we'll update our instruction set architecture and actually recompile the program we have right now for the new 16-bit instructions we have created. Thanks a lot for watching, like and subscribe if you'd like to see more of this, and see you next time.